In this lecture video, we are going to take a look at atomic structure and average atomic mass. Since when we talk about chemistry, right, we're looking at the change and also the property of substance. So atom would be the fundamental building block of substance. So we are going to have to learn about their structure first. Okay, so please read the OER textbook chapter section 2.2 for more detail of this topic. The homework that associated with this chapter section is listed here. Before we look into the structure of an atom, I would like you to actually read about the discovery of subatomic particle first. So that way you see what are the experiments associated with, like discovering the structure of an atom. Okay, so you're gonna see several theories associated with this as well. Please do the self-study on this section. Okay, so this is going to be part of section 2.1. You will need to go to OER textbook and read chapter 2.1 and answer the exercise. Okay, so the answer key of this will be put on Moodle. So pretty much you are going to turn to OER textbook page 49 and read all the way through 62. Okay, so after you finish, then you can answer this exercise 1 and 2. After you're done, then you can check your work and answer against my key that post on Moodle already. Okay, so that's under self-study reading assignment right there. Okay, so to check your understanding. Okay, so after you finish, then you can start watching this video. Okay, so before you watch this video, though, I have a quick before class activity for you. So in this section, you will need to read the OER textbook first to just get used to which terminology that we are going to use for this chapter section and also throughout the term as well. Okay, so the before class activity that you will need to do is to read the OER textbook chapter 2.2. After you're done, then you will need to complete the so it would be this page right here, 63 to 71. Okay, so after you finish reading, then you will need to complete exercise 1. Okay, so this one is going to be definition of this term right here. Okay, so that list is, you just need to match them. Okay, so after you finish matching all this, right, so it's going to evaluate whether you after you read it, you understand it or not, right? So after you finish, then you can check your work against the answer key that I post in Moodle. Okay, so right there. According to the current atomic theories, we now know that atom composed of electrons, proton, and neutron. These are what we call subatomic particles. Okay, so electron and proton has electrical charge. Okay, so they report in Coulomb, which is the electric charge unit. Okay, so these are the charge of electron and proton, and neutron is going to be neutral, has zero charge for neutron. So you probably noticed that the number for the electronic charge of electron and proton is a little bit difficult to use, right? Because it's a number with the exponent. So we are going to pretty much talk about the charge of electron and proton in terms of the relative value. So if you divide these two by each other, you are going to see that the relative charge of electron and proton, there would be -1 for electron and +1 for proton. Note that the value of the charge for electron and proton, they are the same. However, the sign would be different, right? Electron would be a negative charge and proton would be a positive charge. Okay, so according to this, right, so after you get the relative value, you're going to see that electron would be -1 and proton would be +1. Okay, so this is what you need to know. Okay, so neutron would be 0. Okay, so you will need to only memorize the relative charge. So now talking about the charge already, the next thing we're going to take a look at is the mass. Okay, so the mass in grams for electron and proton and neutron listed here. Okay, so these report in grams. Okay, so again, when you're looking at in grams, is also have a lot of numbers as well, so it's not very convenient, right? So we are going to define another unit that help us to see this mass better, right? So it's just going to simplify this number right here. So what we are going to use is we are going to use the atomic mass unit, where we define that these many grams, right, is equal to 1 AMU. So therefore, if you divide this number right here by this conversion right here, right, you are going to get the amount in AMU. Okay, so the atomic mass unit, or U in general, so you are going to probably notice that the mass of proton and neutron are a lot greater than the mass of electron by almost 2,000 times, right? So in this case, you probably notice that the mass of an atom are going to come from the proton and neutron only. Okay, so when we talk about mass of an atom, we are going to only focus on the number of proton and the number of neutron. Okay, so we will not looking at the electrons, because electrons are almost 2,000 times lighter than proton and neutron. Okay. Note that for neutral atoms, the number of proton and the number of electron have to be the same, right? In order for that charge to cancel each other out. So therefore, the overall charge of a neutral atom will end up equal to 0. Okay, so also another note, the number of proton will help you to determine what would be the type of element. Okay, so each element that lists on the periodic table, they have different number of protons. Okay, so that means if you change number of proton, you are going to end up changing the identity of the element. Okay, so the number of protons for specific element will always stay the same. Okay, so if you change the number of proton, you are going to end up changing the type of element. Next thing I would like to talk about is isotopes. Okay, so isotope of an element have the same number of protons but different number of neutrons. Okay, so which imply that isotope would be the same type of element because they have the same number of proton, but they are going to have different mass, right? Because what contribute to the mass would be the number of proton and neutrons. So in this case, isotopes are going to identify by their mass, right? So they're different masses. So you might wonder, well, if isotope is of the same element, then how can we differentiate each isotope, right? So the answer is we are going to use an isotopic symbol or nuclear notation to differentiate between each of the isotopes. Here is an example of 3 isotopes of hydrogen. Okay, so protium, deuterium, and tritium. You probably noticed that these atoms, right, contain just one proton that is represent hydrogen atom, right? And these 3 atoms contain the same number of electrons as well because these 3 atoms are neutral, right? So they are going to end up with the same number of electron and proton. So that way their charge overall will be 0, right? But the difference between these 3 atoms are different in number of neutrons, right? So in this case, protium would be lighter than deuterium and deuterium would be lighter than tritium because as you increase the number of neutrons, you are end up increasing the mass of an atom, right? So that means in this case, these 3 isotopes of hydrogen, tritium would be the heaviest and protium would be the lightest. When you're looking at hydrogen gas in nature, you are going to discover that majority of hydrogen gas going to compose of protium. Okay, so and around 0.01% would be deuterium, and a trace amount would be tritium. And also, it's turned out that tritium is going to be the unstable isotope, which means is radioactive isotope. So the reason why we have this tritium in nature is because that in upper atmosphere, right? So the atmospheric gas, when it reacts with cosmic ray, is going to actually generate this trace amount of tritium in nature. As here are more example of isotope of some common element. So I'm going to talk about oxygen, carbon, and potassium. Okay, so first let us take a look at oxygen, right? So oxygen gas that we breathe, right? So in nature, you are going to see that it's going to contain 99.8% of oxygen-16 isotope. Okay, so and there would be like a small amount of oxygen-17 and 18, right? So these list percent right here is indicate how much is occur in nature. For example, if you have 100 grams of oxygen sample, right? So 99.8 grams is going to be from oxygen-16, and the rest of those would be oxygen-17 and 18. The weight average of these 3 isotopes together, that is going to represent the average atomic mass for oxygen that we report right here. Okay, so the top part right here, this number, the whole number is going to represent the number of proton for that element. So that means if you looking at oxygen, right, it's going to contain only 8 protons, for example. And again, the number with the small point here is going to represent the average atomic mass for oxygen, which is coming from the weight average of these 3 isotopes. One thing I want to point out is that if you look at this, right, so oxygen-16 contribute to the most of the oxygen sample. So that's why when you're looking at the average mass, right, so it's going to come out to be close to the oxygen-16 because oxygen-16 contribute most to the mass of the oxygen sample. Okay, so same thing for carbon as well. So carbon contains 3 isotopes that found naturally. Okay, so you probably notice that carbon-12 contribute the most to the carbon sample, right, in nature, so 99.8%. So that's why the average of the atomic mass of carbon would come close to the carbon-12 because of that, right, because it contribute most to what is found in nature. Right, so carbon-14, which is a radioactive isotope, is produced in the upper atmosphere where the atmospheric gas, right, got bombarded with the cosmic ray, and that is going to end up generate carbon-14. Okay, so when plants do photosynthesis, they convert carbon dioxide into sugar. So this carbon dioxide gases are going to contain carbon-12, carbon-13, and also carbon-14 as well, right? And then when we eat plants, right, we are going to obtain carbon-14 from that. Okay, so that means in our body, we do have carbon-14 radioactive isotope in a trace amount in our body as well. Once the living organism die, right, they are no longer intake any more carbon-14 from their dietary, right, because they die already. So that means there will be a certain amount of carbon-14 that later on, because this isotope is radioactive isotope, so therefore they are going to decay. So the time that used for carbon-14 to decay, right, can be used to determine the age of the organism that once. And this technique is called carbon-14 dating. And archaeologists use this technique all the time to determine the age of artifacts. The last example is potassium. Okay, so in nature, there are three available isotope available for potassium. Okay, so potassium 39, potassium 41, and potassium 40. So the average mass of this, okay, so if you do the weight average of these three isotopes, it's going to come out to be 39.1. Okay, so that's the average mass. Okay, so you probably notice that this average mass comes first to potassium 39 again, because potassium 39 contribute most, right, to the potassium sample that are available. Okay, so again, this top number is going to represent the number of protons. So for potassium, there are 19 protons for the potassium element. So that's what it means. So you probably noticed that potassium 40 is a radioactive isotope. So that means any food that contains potassium, for example, banana that you eat, right, is going to contain this radioactive isotope as well. So that means when you eat food, right, you are going to end up consuming carbon-14 and also potassium 40 as well. Okay, so from your dietary, it's turned out that 10% of the average annual radiation exposure comes from our own bodies, because our own bodies contain carbon-14 and also potassium 40 as well that can decay, right, to give radiation. But the reason why we don't feel anything because the amount is just not detectable. Okay, so it's very low. The next thing we're going to take a look at is going to be the nuclear notation that help us differentiate between each isotope since they are the same element. Okay, so what we are going to do is that we are going to need to indicate the mass number. The name imply is the number that is going to contribute to the mass, right? So that means those numbers are going to come from the number of proton and the number of neutron. Okay, so Z is the atomic number. It's a number that tells you about the identity of an atom. So this one is going to be the number of proton. Okay, so X would be the chemical symbol for that particular element. Okay. So for the number of proton, as I mentioned before, you will need to look up on the periodic table. The whole number would be the one that is going to be represent proton, right? So for example, hydrogen would be 1, right? Boron would be 5, right? So boron contains 5 proton and so on. There are several formats of periodic table. Just know that atomic number is always going to be the whole number on a periodic table. It doesn't matter what format that you see. Okay, so it's always going to be the whole number. Again, the same elements will always have the same number of protons. Okay, so if you change the number of protons, you are going to change the type of the element. So never change the number of protons. So another way to represent this is because the number of protons, we can look it up on the periodic table. So most of the time, scientists can also omit that in this form right here. So this form can be written as chemical symbol dash and just write the mass number right away, because each isotope, they have the same number of proton anyways, right? So as long as you know the chemical symbol, you can assume that their number of proton will be the same, right? So the difference would be the mass, because they have different number of neutrons, right? So therefore, in this case, you can use chemical symbol dash and then the mass number. For example, fluorine, right? If you want to know what is atomic number of fluorine, you will need to look at the number of protons. So there are 9 protons of fluorine. So there are several isotopes of fluorine as well, but I'm going to use fluorine 19. So I'm going to specify 19 in this case. There are fluorine 17 as fluorine 18, but in this case, I'm just going to use one isotope, which is fluorine 19. Okay, so in order to represent this in other form, you can do fluorine, right, dash 19. Okay, so you can omit the number 9 because that number, you can look it up from the periodic table. Next, we are going to take a look at the subatomic particle for this isotope, right? So for proton would be 9 because it's fluorine, right? So now what about number of neutron and electrons? So in this case, the number of neutron will come from the mass number, right? Minus the number of proton in order to obtain this number of neutrons. So therefore, it's going to be 19 minus 9. So the leftover would be the number of neutrons. because together, again, the number of neutron plus proton, that is going to tell us about a mass number, because only proton and neutron that contribute to mass of an atom. What about electrons? So as I mentioned before, for neutral atom, the number of proton and electron have to be the same, like because the charge for those two have to balance each other out or cancel each other out so that the atom would be neutral, right? So therefore, in this case, the number of electron would be the same as the number of proton. All right, I would like you to pause the video now and complete exercise 1. When you finish, then let's resume the video again to check your work. Now let's check your work together. Okay, so this element contains 6 protons, and that is going to be carbon. Okay, so carbon contains 6 protons. So 6 would be on the bottom to represent the atomic number, which is the number of proton, right? The mass number would be proton plus neutron together, therefore equal to 12. You can also write as C-12. This isotope would be neutral because the number of electron is the same as number of proton. Okay, so the second one, 6 proton again, so therefore in this case, it's still going to be carbon, right? But the mass number would be different now because we have different number of neutrons. So in this case, it would represent carbon 13. Next one, it would be carbon 14, right? Because you add 6 and 8 together, so it will be carbon 14. These 3 isotopes are neutral because you have the same number of electrons. All right, let's pause the video again to complete exercise 1, number 2, A, B, and C. Okay, so, and then resume the video when you finish. All right, let's check your work together. So for the 2A, right? So for chlorine, proton would be 17, neutron would be 18. Copper, proton would be 29, neutron would be 34. Antimony, proton would be 51, and neutron would be 70. Next, compare the number of protons and neutrons. As the number of protons increase, what do you see, right? So as this number of protons increase, right? So what do you see for the neutron? Well, it's turned out the number of neutron also increase as well. Next question, why do you think the number of neutrons is not generally equivalent to the number of protons, right? So if you think about the charge of proton, right, they all are positive. If you have a lot of positive state together inside the nucleus, are they going to attract or are they going to repel? Well, the answer is they are going to repel because they have the same charge, right? So therefore, in this case, as the number of protons increase, we need more neutrons to separate out the positive charge. So that way you have the stable nucleus. If the nucleus of an isotope don't have enough neutron to separate the positive charge, right? So that nucleus would be unstable, and that isotope is going to be the radioactive isotope. And the unstable nuclei can undergo several types of decay to generate a more stable nuclei, right? So, and the product of this decay can be used in several applications. Okay, so for example, as you read from the reading assignment, right, when you read about the Goldford experiment, right? So the Goldford experiment from Rutherford used the alpha particle, and this alpha particle right here is going to come from the unstable nuclei, right, or the radioactive isotope, right? So other application of these unstable nuclei or the radioactive isotope can be found in several applications, such as smoke detector, or like gamma ray sterilization, or like radiation therapy, and so on. So next, I would like you to apply the concept of nuclear notation to help me determine the number of proton, neutron, electrons, atomic number, mass number of given nuclear notation, or figure out what would be the nuclear notation, right? So let's complete this table, right, and resume the video when you finish. All right, let's take a look at your answer together. Okay, so for titanium, right, so in this one, atomic number would indicate the number of proton, and mass number would indicate number of proton plus neutron. So therefore, in this case, because we see the number 22 right here, right, the bottom part is going to tell us about atomic number, and that is going to represent the number of proton. And because this atom is neutral, so therefore the number of electron would be 22. Okay, so the same as the number of proton. And for the mass number, it would be 50, right? Because this number right here tells us the number of proton plus neutron. So together, if you subtract the number of proton from the mass number, you are going to obtain the number of neutron, which is 28. All right, so next one. So I'm going to assume that everything here are going to be neutral. So it's giving us the number of electrons. Okay, so remember the neutral element are going to have the same number of proton and electron. So therefore, in this case, we know that the number of proton would be 41. And since proton and atomic number are the same, so therefore atomic number will also be 41 as well. In order to figure out what would be the chemical symbol for this, we will need to look up the periodic table, right? So according to the number of proton, this come out to be niobium, so Nb. What would be the mass number of niobium then? This is when you will need to add proton together with neutron. Okay, so it's come out to be 93. So in order to complete the nuclear notation, right, you just need to include the atomic number and also the mass number as well. All right, let's say the next one together. Okay, so that's zinc 66. So again, so you can either report in this form or this form. It doesn't matter. Okay, so they both are represent the same thing to me. Okay, so next one would be barium 134. And last one, this would be the number of subatomic particles for neon. If your answer are different from what I have here, please do not hesitate to reach out to me, okay? Next, we are going to take a look at ions. Before you look at the neutral atom before, in this case, ions are going to be atoms or groups of atoms that gain or lose electrons. Note that only electrons, that please do not change the number of protons. Okay, so ions are going to lose only electrons, not the protons. Okay, because if you change proton, you are changing the type of element. Okay, so we are going to change only the electrons. So if an atom gains electrons, it will have a negative charge, right? Because electron is negative. If it gains more negative, the overall would be negative. Okay, so these ions would be called an ion. If an atom loses electrons, okay, so remember before you have a number of proton the same as the number of electron. If the electron is being taken away, you are going to have less negative. Therefore, the overall charge of that atom would be positive, right? So we call this positive charge of an atom cation. Okay, so this ion would be cation. So there's a joke here for you to remember, right? So cation is an ion with positive charge, right? So so that's how you can memorize this. Okay, so now to represent ions, okay, so we are going to write chemical symbol. Okay, so I'm going to look up chemical symbol for potassium. Okay, so potassium is not P. Okay, so potassium is K. Okay, so if potassium lost an electron, that is going to indicate by a positive charge, right? Because you're losing a negative, so the overall charge is going to become more positive because you have less of electron in an atom. So that positive charge is going to be indicated on the top right corner of the chemical symbol. Okay, so this would represent an ion of potassium. Okay, so this is potassium ion, or what we call potassium cation. Okay, so now what about if you have phosphorus? Okay, so now we can use P. Now P represents phosphorus. This phosphorus gain 3 electrons. Remember, gaining electron, it will become more negative, right? So that gaining 3 electrons is going to become 3 negative, and we are going to again indicate the charge at the top right of the chemical symbol. So therefore, this phosphorus right here is an anion because it gains electrons. All right, let's take a look at this example together. So here we have neutral atom of carbon. We have an ion of carbon. We have cation of carbon. Okay, so let's take a look at the number of proton. Okay, so these 3, because they are carbon, so therefore the number of proton, they are going to be the same. Now let's take a look at the first one. Okay, so first one, carbon, this is doesn't have any charge indicated. So therefore we are going to assume that this carbon would have the same number of electrons as proton. So what about carbon 4- or the anion of carbon? So this one, you are going to again have 6 proton because still carbon, right? But it's gaining 4 electrons. So therefore, the total number of electrons would be 10. This carbon right here, 4+, is indicated that this carbon lost 4 electrons. So therefore, you are going to subtract 4 from the original number of electrons. But you are going to end up with only 2 electrons. Let's take a look at the next example. Okay, so we are given a table that contains the number of neutrons, protons, and electrons. Okay, so these are an unknown atom. So we want to find out the isotope of A. Okay, so we want to find out isotope of A. So this one A right here. Okay, so you need to go back to the definition of isotope first, right? So what is isotope? Isotope of the same element would contain the same number of protons. So therefore, in this case, we need to find out the candidate that contains the same number of protons. And that is turned to be C and E, right? We can eliminate B and D because B and D have a different number of protons. So now which one would that be? And remember isotope, they have to have the same number of proton, but they have the different number of neutrons. Right? So in this case, if you compare between C and E, right? So C have different number of neutrons compared to A, and E has the same number of neutrons as A. So therefore, in this case, the isotope of A would be C. Now, what about an anion of atom A? Okay, so an anion of the same type of atom, they will have the same number of protons, but different number of electrons. So in this case, if you're looking at E, right, so you will see that E contains the same number of neutrons and protons, the same as A, right? But A and E have different electrons. So the answer of an anion would be E, but because E contains one more electron or more electron than A, right? So that means E is going to be an anion of A because gaining electrons.